Okay guys, we are talking in terms of chemical thermodynamics. Alright, and in chemical thermodynamics we have already seen that in isothermal state there is transfer of Q to the system from surrounding. It's either giving to system or taking from system to maintain isothermicity. That's what we saw in isothermal state in our earlier videos. So Q was involved. Now since Q was involved, so del H is involved. Alright, enthalpy is involved. Now we have already derived first law of thermodynamic equation, which is Q is equal to del U plus P del V. Now Q is linked with H, so we can also modify it to H is equal to U plus PV. Simple equation. Now suppose we carry out a reaction A plus B giving you C. Now this is initial and this is final. So initial has its enthalpy, internal energy, volume and number of moles. Similarly final also has its enthalpy, internal energy, volume and number of moles. It's N20. So if we take the difference between these two, it would be del H, del V, del U, del L. That is final minus initial of respective parameters. Got it? Okay. So now, we can modify this equation in terms of final minus initial. So it would be del H is equal to del U plus P del V. Del H is equal to del U plus P del V. Now del H, del U, del V, I already explained. Now P del V can also, we know as per gas equation, PV is equal to nRT. So instead of PV, we can also write it as nRT. Now mind you, we are talking in terms of chemical thermodynamics and it's all in gaseous state. So this number of moles would be change in number of moles of gases. Alright, so del H, del U as it is, whereas here we get RT and del N, change in number of moles, del N. Alright, let's try and understand some equation where del N, now this is what is work, where we find where work is positive, work is negative or no work is done. Alright, now let's take this example. Now it is this solid carbon reacting with hydrogen giving you ethane. This is gas, so are involved in our calculation, but this is solid, so solid we are talking in terms of gaseous state, so solid is not considered. So what is the difference in number of moles? Here in product we have got 1 and here we have got 3. So 1 minus 3 gives minus 2. So N2 here is less than N1. So del Ng, number of moles, difference in number of moles of gases is negative. So work would be negative. So if we substitute, this is formula for work. If we substitute, it would be negative. Alright. Okay. Now when we take the second example where carbon solid reacts with oxygen gas to give you carbon dioxide gas. Again solid, not included in calculating number of moles. Alright. So 1 mole of oxygen giving you 1 mole of carbon dioxide. So N2 is equal to N1. So del Ng is 0. 1 minus 1 is 0. So work done in this process, is 0. Alright. And in this case, when we take N2O4 dinitrogen tetroxide gas giving you nitrogen dioxide. Now 1 mole of gas giving you 2 mole of gas. So del N is 2 minus 1, that is positive 1. Here N2 is greater than N1, so del Ng is positive, work is positive. Now how does it make difference in del H? Obviously when it is positive, this is added to del U. When it is negative, this is subtracted from del U. So enthalpy, it would be reduced when this value is negative. Enthalpy would increase if this value is positive. So as we saw here, negative. So this value would, enthalpy value would reduce. Why? Del U, from del U we would be subtracting that value. If it is del Ng is 0, then this parameter would disappear totally and del H would be del U for this reaction. Alright, so in this reaction we would find del H would be lesser than del U because this value would be subtracted as del Ng is negative. Whereas when we see this reaction, in this case work is 0, so this would be 0. So for this reaction del H would be equal to del U, and for this reaction, since it is positive, to del U we would be adding work, so del H value would increase. Alright, so that is how we would be seeing in numericals also. All right, so this is all about enthalpy change. All right, okay.